Okay, so now groundwater. This is very special to me because it's geotech is very cool. I mean, the fact that you can sort of like look at percolation in a very precise way. That's, to me, that's master level thinking. Percolation is, when you just think of percolation, you just think, oh well, put water in coffee and stuff and put it together. But there's a lot of complicated things related to it. Because you can actually have water, or can you imagine being able to, let's say if everybody's starving or they need water or whatever, you go ahead and use your engineering skills, and then puncture the ground, and then water starts flowing through that thing. That's the power of groundwater, of Darcy's law equation, and the groundwater engineering. So let's go ahead and go through this a little bit. So right now I want to focus on something called Darcy's law. And so Darcy's law, from our point of view, is a differential equation, which is Q. Well, it's not. This is not the differential equation, but Darcy's law comes from a differential equation. So in this case, if you have Q equals minus K times A times dH dx, we're talking about H being the total head at any given point. So and then here we're talking about a spatial dimension. So for example, if you have I want to say, you could have some really strange situation with some kind of soil, I don't want to. So you might have this, and then, or you might have a dam. That's a better way to put it. You might have a dam, and then it only goes out this far, maybe, but it punctures the ground, and yet there's water here, right? So, in this case, you might have water flowing like that, and you might have some gravel here. So it might go this way. And so in this case, what this predicts is it says, well, the total head has something to do with, what this predicts is it predicts how much flow you have. So if this is considered dx, little dx's, right? This is dx all across, right? Then you'd be able to predict how much discharge is through some section of the flow. And it could be two-dimensional, it could be one-dimensional, but you'd be using this equation to predict that. And the head is all elevation, so it doesn't matter where you're at. So if you want to get this whole piece here and say, okay, from this whole piece, I want to know what Q is. And so then you would use this very precisely to determine that. And you might say, what's the total discharge of the whole thing through this region? And as a result, you would still use this. I mean, it's amazing. So, but just to let you know, the total head, when you say DH, you're talking about some elevation. You're talking about a y direction. So this is yx. You're talking about the value of the total head at this point versus this point, but with respect to the y direction. It has nothing to do with x. So, but whereas dx has to do with the direction of the flow itself. So this is very powerful, and you can see that it's you'll see I want to say sand, and you'll see this all over the place. So that's the case, yeah. And I want to say that it does come from a differential equation. In a way, this is a differential equation, but it's not very precisely defined. Like, technically, this is dv dt, right? So, it's not very precisely defined. But if it was in a strong form, like, I consider this a weak form, because all you can do is write an integral, right? So if you had a strong form, it would be a lot more close. It'd be a lot more defined, a lot better. So, is it weak form? Is it strong form? I'm not sure, but I would consider this weak form. Anyway, it's not very close. It's not very defined very well. I guess it is strong form. I would have to go back to my studies, but this is not strongly defined. So, but we can still use it for our purposes. So whenever we're talking about Q, we have to keep this in mind, is that we define it for a region. So such a region could be anything from minus infinity to infinity, you know, in the x, like in the x, right? So you could say, well, x can be, in my case, x can be in between minus infinity and positive infinity. And then y can be within h1 and h2, something like that. So if that's the case, we're going to be using this in a very, but we're going to be a little bit more practical at first, and then we're going to work our way up. So, but we need to define Q first. So before we do anything, then from that, we determine our total head and our, spatial dimension x. So x doesn't necessarily have to be this x, but it could be anything. So you say dx, you're talking about any direction, any length. So let's go ahead and move on. And by the way, all these things should look familiar to you, I guess. I don't know. You have A, K. K is the hydraulic conductivity. H is the total head. X is just the dimension. You're going to be length dimension in the direction of flow. So anyways, let's see an example. So in this case, it says a soil sample with a permeability of 5 times 10 to the negative 6 inch per second soil will be tested using the pipe setup shown. The pipe's diameter is 2 inches. The 10-inch head differential will be, I don't even know what that says. Will be maintained. Okay. The volume of flow is most nearly what? Okay, so if you're trying to get the volume of flow, you would think like it should just be a volume, but it's actually a discharge, a form of discharge, inch cube per second. So remember how we said we should define our region for it? So in this case, Q's region is going to go all the way from here all the way to here. Now, it doesn't have to be X or Y or whatever, right? But our Q is going to be within this location. And it's going to be extending. So it's going to have a finite thing. It's going to be extending all the way up here. In some ways, I'm doing a what you might call a control volume thing, but I think this step is important because you might get confused. Like, so this is what we're defining for Q, and I'll just call it a Q region. So because this is our Q region, that basically you would say, well, let's use Darcy Weisbach, right? K A D H dx. Okay, so now that we've defined this, there's no confusion for us that we're looking at this portion somewhere in this region, right? So if that's the case, what you could do is you could say, well, what we're doing is we want to know will be maintained. So the volume of flow let's see a soil sample. So if we assume it's the same everywhere, the same discharge, technically because we're talking about the soil itself, this should be Q. I'm sorry. This should be Q, our Q region. So if that's our Q region because that's the soil, then we're going to call this A. We're going to call this B. So what we could do is we could say, well, this is approximately minus K A times delta X, or H over delta X, right? Over of the soil piece, right? So delta H, which is the head, right, is going to be the difference between here and here, the head. So because they said it's going to be maintained, the 10-inch, then it's just 10 inches. we don't have to do any work for it. I mean, if you were to say it's here and here, right? What we can do is, what we would do is technically say, well, we need to know what this is, and then we also need to know what this is. So that is just simply this, based on what we see, and then also based on what they give us. So obviously that's 10 inches. Delta X, remember, is the amount of length that goes between what you're looking at. So in this case, it's 20 inches. Let's assume that there's no flow outside it. That's why I chose this to be my region. So in this case, we would have that the hydraulic conductivity is 5 times, that's the permeability. So the permeability and the hydraulic conductivity, I don't know how they're related, but I think they're the same thing. Permeability and hydraulic conductivity are the same thing. So in this case, so if we do that times area is 2 squared times pi over 4 times delta H. So in this case, it would be 10 over 20. And then times, and then that's it. So you should be able to get your answer from that. So it's about 7.9 times 10 to the minus 6 inches cubed per second. And I think that's the answer. So, yeah. I guess in this case, it's the same thing, the permeability and the other thing, hydraulic conductivity. I don't know enough to say whether it wasn't. I was trying to figure it out, but I guess not. So yeah, they're the same thing. So let's move on. Okay, now here's another example using Darcy's law. So now that we have this case, it's might be kind of difficult. It says, so let's just go straight to the problem statement. The loss from seepage through the soil profile in 1 year will most nearly be what? So let's go to the seepage thing, right? The seepage, let's see. So this one has units of meters cubed. So it's going to have to be, let's see. And we're going to be using the same Darcy equation. But instead we're going to be multiplying Q by the volume. So let's remember again, let's define our Q region. And so in this case we have a Q region of let's see, it's just going to be the soil itself, the top of the soil, the bottom, and then where the sand is, and then where the sand is, right? Because when this is supposed to go through the sand, right? Hold on. Through the soil, then we have a certain discharge, right? And so we're going to find out how much volume goes through that in 1 year, right? So let's determine what that is. So let's read this problem statement. A concrete dam impounds reservoir water as shown. The standing water depth is 1.5 meters. The soil layer under the reservoir is underlain by a highly porous sand layer. The sandy layer at the bottom of the soil profile has horizontal drainage and zero pore pressure. The water level of the reservoir is constant. The total area of the reservoir is 1,000 meters squared, and the coefficient of permeability is 4.7 times 10 to the negative 6 millimeters per second. The loss from seepage through the soil profile in 1 year will most nearly be what? So let's go back to our Darcy equation, right? So in this case, you have dH over dx, right? If we talk about the flow in terms of what they gave us, then we're really talking about what we have. We're really talking about this per second, whatever they gave us. So we're gonna have this per whatever per second. So because this is happening per second, we were gonna have to multiply everything by I believe it's going to be a very large thing. It's 3,600 seconds per, I believe. Is per hour. So you have per and then there's 360. It's going to be 3 million. I mean, 31,104,000 is what we're going to be multiplying by, because that's how many seconds there are per year. Even though that seems gigantic, yeah. Well, it's a little bit more actually. Hold on, I meant to say 365. So yeah, it's going to be a little bit more, but so we can just say there's 315 or 31,536,000 seconds per year, right? So in this case, we're going to be multiplying it to get it per year. So all you got to do is say Q equals, and we've defined, this is our Q boundary. So, and we're going to get it for that. And so this is going to be 4.7 times 10 to the minus 6 millimeters. We got to be careful with units here. So we got that. We got area 1,000 meters squared, and then dH dx, and then this is just per s, right? I'm gonna multiply everything after. So h and x are gonna be the hard thing. H has to do with the difference in head between here and here. For all practical purposes, let's define our datum here. So datum. And if you just sort of say, okay, well, at this point we have a total head of, for the first one, for number 1, you have, I think the total head should be 0 plus 0 plus what? Go ahead and say, I'm just going to, strangely enough, it is, I'm not sure why, but I just know it's 0. So pore pressure, 0 pore pressure. That's the idea. That's why it's 0. So in this case, you have that. So obviously delta H is 8 meters, right? Because it's 8 meters minus 0 meters. So, and then now we have X, right? So dx is 6.5 meters, because we're talking about what the distance where it flows. I don't know if I defined it, but because the distance is in the direction of where it flows, it's 6.5 meters. So ultimately what you get for Q is, this thing is that dH over dx is roughly delta H over delta X, which is 8 divided by 6.5. And so when you plug everything in, you're going to get, so this is approximately 182 meters cubed, and that's the right answer. So, oh, I'm sorry, this is, if you multiply it also by this number. There's just so much going on, it's just hard to squish everything, so this is the answer. So let's move on. Okay, now this is where we're going to get to. This is the beast. I went over a lot, and I'm sorry I didn't. Okay, let's move on. So, with chapter 11 continued, we're gonna start the well drawdown, which is probably the most. It's not the most important thing, but it's the most complicated portion. This is gonna require. I'm just gonna say it right now. It's gonna require calculus if you really want to understand it. And I think we should really go over some of the derivation, because it is important. So earlier I said that the Darcy-Weisbach equation can be, or the Darcy's law can sort of be seen as a differential equation, in the way that in the way that we use it to determine the flow and everything else, some other information. So I wasn't exactly specific in what I meant by that, and what I meant by weak form, strong form. Actually, if we're going to write it out, so you see all this stuff, right? Let me just back up for a moment. You see, look, before we get to that, I wanted to go over the Darcy's law. So remember, it's this thing, right? Right? So this is actually, if you look at it from the point of view that this is constant, it's not constant per se, but if you look at it from the point of view that this is a constant, as well as everything else here, then this is considered a weak form, and 1D diff EQ. And so from that point of view, that such that these are constants, we can extract information from that point of view. Now this is completely mathematical, by the way. It's kind of like saying, well, let me set 2 equal to 4 times dy dx. It's similar to this, and this is completely mathematical. Why? Because we know what we know what 2 is. It's 4 times dy dx, and 2 is a number which is trivially is such that dy over dx is 0.5. So it's similar to this in that sense, in the sense that that the constant here is an unknown. And so it's very strange because I've never seen an equation like this other than this. But it's nothing more than this. It's like, so it's similar to this. You can also see it like maybe a equals b times dy dx, and such that b and a are constants, right? So if a and b are constants, and you want to determine what it is, you would want to know what dy dx is. But if you don't know what they are, like, how do you get it? You might be thinking, like, how do you determine all this stuff? Because it is possible that, what am I trying to say? That if you solve this stuff, or because when you look at this, right, it's possible that we have boundary conditions. And if we have boundary conditions, then this can be solved. This can be solved in a way that eliminates this unknown. So the boundary condition, if we have one boundary condition, it can solve what this is. And that's what we're going to do here. So this is the easiest way to look at it. And so let's go ahead and get rid of this stuff. And I'm actually going to get rid of everything. So from this point of view, let's just keep this in mind. So let's go on to the next thing. So in this case, we have a well drawdown unconfined aquifer. So you get this formula, right? For the purposes of FE, if you know that it's unconfined aquifer, which means that you don't have anything trying to push it. So what do I mean by that? So what I mean by that is, if you have a confined portion, it means that that confined portion is going to flow in a way that is rectangular. So a confined portion would allow you to say, okay, well, I'm going to create a boundary condition myself, so that even if water is over here, I'm going to block it in such a way that it can't flow up here. Instead, it would have to flow this way. I'm forcing the flow of water. So this is what confining is. I'm forcing the flow of water to go this way, and not this way or this way, but specifically this way. Because if you was able to go this way, then it would make it weaker. Like, if it was able to go this way, you're not extracting as much water. If it's more confined, it's going to have a greater flow at this point. So that's what confining is. But in this case, when you don't have confining, all you do is the influence starts at the point at which you're drawing from. So in other words, hold on a second. Oh shit. So if it's unconfined, this portion that would start to flow this way, it would be a more natural thing. So there's no way to calculate what this is, but if we assume that the flow is zero at that point, because, well, let me put it this way. Carol? Okay, so let's draw this up again. So remember, for the confined thing, we have a solid here, right? This is confined. In the confined case, you only have flow going here, but here's the kicker, is that you still have an elevation head that's changing. So maybe some water might go through here and here, but in the confined case, we're assuming that the flow is completely in this location and that it's mostly not here. So yet as you get away from this point, you have changing elevation heads. And the reason for that is because of I think it has to do with the flow, like you do have changing heads as you go out, but see, the thing is, you have to be, that's a matter of research. We'll go over that a little bit later, but let's keep going. So this is the discharge that would be going through a this is the formula for the discharge that would be going through an unconfined location, right? So, but this is confined. The only reason why I brought it up is because of that difference. So because we assume that it's only going through this section, we assume that as you are talking about the area, in terms of getting the discharge, the area is going to be a function of R, but it's no longer in the confined case. It's no longer a function of H. It's just a function. It's a function of the depth from here to here as you have variations along R, because we assume that it's the only areas being affected in the pipe, because this is a pipe. This is going to be an impervious portion, like clay or something, or just really hard clay. So, and this is soil, obviously. This might be like sand. This might be also sand, but basically this is impervious. So, and then this thing is the bottom of the pipe. So it would have something like that, but it's going to be more important as we move on. But for now, let's try to derive the equation for this because it's important. So for confined, you assume that the flow here, as the heads are changing, it corresponds to the height variation of that flow affecting the pipe as it goes up. So let's go ahead and erase all this. Oops. Oh, shoot. Okay, now let's... Okay. Sorry, so now let's go ahead and erase all this stuff. And there you go. Another problem. All right. This is yet another problem. I didn't know I was going to have this. Now it's permanently there. Jesus Christ. Okay, so I guess I'm going to have to do that. So, I don't have to do that. So I'm going to do this, say no, don't save. Because we're still recording, right? Good. I'm going to go back to the PowerPoint. Jesus Christ, man. Jesus Christ. So, let's go back to that. Okay. Review. Or I should say slideshow. From Kurt's side. Okay. Here we go. So, now we're going to derive this equation. It's important because these variables, this ln doesn't make any sense when you first look at it. But remember what I said earlier about the formula, right? So we have q is equal to minus k a dh dx, right? So we can treat this as a constant, and as well as this. Now we're gonna have to do something special with a. Let me do something unique here. So if we go ahead and transform this into q equals, and we're gonna, q is gonna be a constant. Why? Let me explain. So q, remember we always have to, when we're working this out, we always have to define a region for q, right? So if we define that such a region to be, in this case, because it's unconfined, to be, so let me draw this again. So, sorry. To be, this is the well, right? So to be, and I'm not trying to confuse or anything, but this, we could say that this whole thing is our Q region. And in this case, we will need to be a little bit more precise, because in this case, our Q region is X, if this is X, Y, right? Our Q region is such that X is minus infinity to infinity, and Y being in between H1 and H2, right? So now, so I am looking at these, how we defined our Q region is, this is true, but the Q region is here. But what you got to understand is that all right. Whew. Okay, so okay, so this is our Q region, right? One thing I wanted to go over to is that I think it might be hard to understand this, but this is our Q, even though this is our Q region, it's not quite like this. It's more like you have to look at it from this point of view, because if you look at the plan view, right, you got this pipe, the flow is going this way. So it's not fair to say that our Q region is simply this. It's the Q region is the volume of a cylinder with an outside and inside diameter. An inside diameter being here, or being this, and outside diameter being infinity, because it comes out all the way. So that's what our Q region is, and that's what this is. So you can transform this into saying it's R being from R1 to infinity, right? And then from, and for Y, it's from 0 to H2 still. So these things are equivalent, but in some ways, because I forgot to, in some rough way, because I forgot to change this. But yeah, that's what it would be. But so now the reason why you're able to see a flow here, and I want to go over this, is because this is perforated, or what you call slotted. So when you look at the pipe itself, because this is a pipe, this is the solid pipe, it allows water to go through it so that it comes upward. So this is a solid piece, right? And so I wanted to describe the solid piece really fast. So if I go ahead and just get rid of everything, the solid piece. Now I know I'm all over the place, but today is crazy. You got so much fucking distractions. Anyway, so you got this thing, right? if this is the solid piece, then it's perforated, which means it's like, it might be like this, right? So all throughout the solid, it's got holes in it, which allow the water to go through it, perpendicular to it, right? The water flows through the holes. And it's like that all throughout the pipe. So this is the solid pipe, solid perforated, slotted pipe, steel pipe, allowing water to flow inside. So perpendicular to it. So that's why that's the case. That's why we're working out the equation that way. It's not like it's coming from the bottom or whatever. This is the way it is. So if I'm going to go back to that equation, which we're going to solve, let's go back to Q equals minus K A dH over dx, right? And by the way, we're going to transform this into just, we're going to transform this, we were starting to do that, to Q of R equals minus K, because K is a constant no matter what, times A of R times dH of R divided by dr. Now there's no, you don't need to do anything fancy to notice to go ahead and do that. It's just the different formulation, different dimensions to explain the same problem. Because as long as you know that A is a function of R, which depends on a circular dimension, then we're good, right? So, so yeah, this is the case. Let me be more particular here. So if this is the case, then we have to rearrange our equation. Now, by the way, I have to be careful here, because remember, we're treating this as a constant because we define our region to, we're defining it to be within a certain region, and so we get to do that. So because remember, it's in within that region, so it's within that region in between here, right, and infinity. So that's our Q region. This is our Q region. And as a result, we're allowed to treat it as a constant for our purposes of solving what this is. So if we're going to get rid of all this, we get rid of this stuff, right? Slotted, so it's able to go inside. Just keep that in mind. Then if we want to solve it, we can go ahead and rearrange the equation in such a way that Q times dr divided by A of R, which you should see, you know that A of R, because the whole thing, now I should draw it out. So because the whole thing is being affected, because it's not confined, water is going through it entirely and is going to go through it entirely. So, and our Q region is the whole thing. So water goes through it entirely, which means that A of R is 2 pi, it's the circumference, 2 pi R1, or R, really, times H. So if this is the case, then we take this divided by 2 pi R H. That's going to be equal to, because I'm just dividing it out, K dH, right? So if that's the case, then, and H is a constant, well, H is not a constant, so we have to multiply it on this side, which means that we could just integrate once we do that. So the reason why we have to multiply on this side is because H is a function of R and R is a function of H. So they have to be, they're independent variables, and you have to put it on the other side as a result. So this is Q being a constant, dr over 2 pi R is equal to K minus KH dH, right? And that's also an integral. So we know that R goes from, is supposed to go from R1 to whatever this portion is, R2, for our formula, because R2 is extending this way. So in such a case, you're going to end up with Q over 2 pi ln of, remember, because of our limits of integration, of R over 2, or R2 over R1, is going to be, and then by the way, this is H1, H2, because we're evaluating our heads to be from one point to the other. So our total head at this location, where R1 is, which is, by the way, this is important because R1 is the radius of the well, and that's always the case, no matter what. Even if you look at the confined. So this is H1 is where the edge of the well is, and then R2 is where it starts to level off. Now it may not say that, but that's what it is. So because remember our thing is infinite. So it says R2 radius to water surface whose height is H2 above bottom of aquifer. So really this is deceptive. That's wrong. It should actually be somewhere around here. So R2 is somewhere around here. They just didn't know how to do it because it's really complicated. Anyway, because the groundwater is clearly levels here, right? So if you get a problem like that, that's from the calculus derivation, then that's in fact true, right? So this is minus k times h. So it would have to be h2 squared minus h1 squared, right? Divide by 2. So the 2's cancel, and you're left with, and you're going to be surprised because this is q equals, you might be surprised, k times h2 squared minus h1 squared divided by ln of r2 over r1. Isn't that just this one? Oh, well, obviously you still have the pi. Isn't that just the pi? I forgot to put that in right here. Yeah. Isn't that just this one? See? If you understand this, that's what you'll get. So anyway, let's move on. All right, let's move on. All right, so now we have the confined aquifer, or well, drawdown well, and as you could see here, as I've said earlier, basically the how do I say it? Hold on a second. So basically the unconfined aquifer, and let me draw that out again. I want to remind you what the unconfined is all about. So the unconfined is basically you still have this well, which is a steel perforated steel pipe or something like that. This is an impervious soil. And you still have soil up above until you get to the ground surface, which could be clay, it could be something like, most likely sand or something like that. So we're going to draw the ground surface. This is a GND surface, right? And in the unconfined case, basically when you put the steel in, it goes from leveling off where it should be, where the water table should just be level, right, to making some kind of curve like this, right? And basically this steel can only influence, this steel pipe can only, that you puncture into the ground, can only influence the disruption of the water table to make it curve this way in a certain area. So it's not going to be like this all throughout. So you would expect that eventually it would level off the way it should always be. So and it converges that way. So if this happens, this is the unconfined. The idea is that you have a ground surface, right? You have this thing, and the water is filling up with, or the pipe is filling up with water, and as it fills up, this becomes less and less curved. So it might start off here, where the curve is this way, and this way, but as it progresses, it's gonna keep going up. So maybe you might have this one, and then this one, and I'll erase these, but you start off that way. And so this is just a representation for where it is typically. So where the water is typically in the pipe, just any given moment. But the idea here is that because it's unconfined, we would expect that the water flow is all throughout the length of the pipe. And so this represents the water flow. all throughout until it gets to the ground surface, of course, because that's so the unconfined case, you have that the area for the flow. So in the unconfined case, you have that the area for the flow is A of R equals 2 pi R times H. And that means basically that your A of R is going to go from here all the way up. So because R is going to be the distance from here to where your water table's at, H is basically the height of the water table. It's the head, it's the total head basically, but and it becomes more relevant when you look at this, when you talk about total head. But basically, because it's the entire thing, you have to make sure that you're accounting for the fact that each point is being affected. So in this case, A of R is 2 pi RH, right? But for the confined case, because of the fact that we expect the flow to only be below the solid that's confining it, so this is the ground surface, and this might be, this is the thing right here, so this is the ground, or this is, sorry, impervious soil, so impervious soil. And because this is the impervious soil, this is like penetrating. If you have a confined portion of it right here, I'm going to say solid confines flow. That is the same thing as saying that the flow we would expect the flow to be only this way. It might seep through a little bit here, but this is how we're idealizing it. We're idealizing it such that there's no flow here. Right? So that it only goes through here, even though you do have a surface like this, and the water table would have to originally be here maybe. So in other words, it would have to taper off like that. Even though that's the case, even though the water table is above where it is, where you have flow, basically, even though you have the flow here, and that the water table is above the flow region, this is the case, and as a result, what we get is that A of R is 2 pi, well, you still have R, I think, but, well, you'll have R, but because it's only in this region, it's B. This is B. 2 pi RB, right? Because you only have this portion that we expect the flow to be. So because of that, and that would be the area of the entire thing. And the other reason for that is because we're expecting that the water table is going to be above the solid region. I mean, if it weren't, then this equation would have to be similar to this. So the assumption here is that the Thiam equation, which is what we're using here, assumption is that the water table is above the solid at time of Q calc. I want to say Q calc as in if this water table were below, then we would apply the unconfined condition, because obviously, well, I want to say that maybe you do and you don't, but just know that this is the assumption, because if the water table were below, you might get a strange situation like I don't know how that would work. Although I think the water table, it would have to show up here. It would have to show up with the curve if it's above the solid piece. So if it was below the solid piece, you would still have this situation where this thing would occur, right? But you wouldn't have a curve. So I guess the equation would still apply. Let's get rid of this. You don't. There's no assumption involved. Sorry for that. There's no assumption involved. Basically, if that's a special case. So if let's say if the water hasn't reached it, so you have something like this. It's a very special case. I mean, if you have something like this, and then it starts to, you still have water trying to flow through it, you would basically have a situation where, I want to say, it'd be like that, but not really, because you still have water. The water table's above it, so in some strange way, it'd be like this. That's how it would be. You know what I mean? So it would have to be like that, but the water would still be going this way, and so you would still assume that this B thing is the case. You would still say, okay, the B thing is the case. You still say A of R is this, and so thus you would still end up with the same equation. I'm just showing you the possibility that the water table is below it when it starts to actually seep in. So let's go ahead and move on. That's a very special case. So if that's what's going on, basically we can then now derive what this equation is. It's the only difference. This is really like the only difference. So once you understand that this is the only difference, you'll understand why this equation is different from the other one. So if I go ahead and just delete everything and still recall, well, I'll try to just get rid of this. Alright, excuse me for that. Something happened and you saw that it erased, right? So whatever was here, something happened to where I was using ink. Let me just test this again. Okay, good. To where I was using, it was just glitching on me, the drawing program, but pad. I don't know what was happening, but basically, if we get back to this concept that A of R is, and hopefully you can keep up with what I'm saying, is this. The other thing that I want to say is that, and we know what Darcy's law is, right? So it's this. Let me just put this more precisely. In this case, it's this. Then basically what they're doing here is, now this is where we have to be kind of careful here. So in this case, in the manual, this is what it's saying, right? It's saying H1 and H2 are heights of piezometer surface above bottom of aquifer. The reason why this is the case is because they're saying basically, well, it's possible that we only care about two spots because maybe I can extract information about the flow and I don't need the entire thing. So it's possible to put two piezometers. You can put one piezometer here and another piezometer here, get readings for that, and then find out what Q is in that section. And so you would define your Q to be something like this. You would have your first thing here, your well diameter is here, your well diameter is here, and this would be your piezometer readings. Would be here, out of the page. I don't know, I'm just being kind of strange, but basically, these would be your piezometer readings. Sorry, not necessarily over here, but because of this, your Q region is going to be all of this stuff. That's what your Q region would be, is this thing enclosing it. So you would still have flow going this way and this way and this way and this way, inward, but your Q region in such a case would be something in between here and here. Whereas with the other case, your Q region was somewhere in between the well boundary and infinity. For all practical purposes, it's infinity because it levels off like somewhere. We don't know exactly where. But in this case, it's simply this. So that's where this equation comes from. It comes from the fact that you can have boundaries in between here. And the limits of and that would be your limits of integration. So, but in the case where we're using the Theorem equation simply to get the total, now this is because this is general, but if we're going to get the total, if we're going to get the total discharge into well, then you would have to modify the equation so that R1 is R well. So just keep that in mind, you know what I mean? So I don't want to go back to verify something myself. This is not, actually this is kind of complicated, but yeah. So so yeah, that's the case. And by the way, as the this is kind of funny because as this increases, right, as you get more and more and more water into your well, you're going to have into your steel pipe. What's going to happen is your Q is going to be decreasing and decreasing and decreasing, and when it gets up to here, because you know that because also H1 would have to be H of the well. So if suppose this were all the way up here, then you would have Q is equal to 0, right? So if you do have in fact that this thing goes here, and by the time it gets here, it's inside the pipe, right? Then you have Q is going to be equal to 0 because H2 minus H1 is going to be 0. Just going over that to give you a reality check, because that's in fact true, right? As it goes up, the Q is decreasing. So you could say something like, if you're going to plot, I don't know what it would look like, but if you're going to plot Q versus, I want to say H1, which means it's going to go up like that, then it might look something like this. I don't know. I can't really. I think it'd be more like, yeah, more like that, but I'm not sure. So, I don't know what the plot is, but that's kind of like what it looks like. So I'm gonna erase this stuff because it's not relevant right now for what I'm gonna say next. So let's just keep that in mind. So if we're gonna derive this, remember this is the constant, and if we're going to rearrange everything, you're gonna have that from the constant, the fact it's constant, you're gonna have that integral from R1, R2, Q over, and remember if you plug everything in, you get this thing, you get 2 pi RK equals, because you plug you plug this thing into here. That's going to be minus this, then it's B, right? B DH R. See, we don't have, this is the difference, because this, remember, this is all confined. This is all confined. In the unconfined case, this would be H. So because we have B here, it evaluates to just H. So what we're gonna have here is Q over 2 pi R K. I'm sorry, K ln of R2 over R1 is equal to minus BH1 minus H, or H2 minus H1. And by the way, I forgot to put my limits of integration here. So as a result, Q is going to be 2 pi K times, or I don't know, the minus can go away if it wants to, but yeah, the minus, I don't know. This is subjective. Just get rid of it. it depends on what you're looking at, I guess. But yeah, I guess that it can be non-trivial. Let's consider that. If you go back to the, yeah, it's definitely minus, but this is technically plus because it's going in. So yeah, I messed up earlier. Sorry about that. This is that, and then times b times h2 minus h1 divide by 2 pi ln of r2 over r1. So as you can see here, this is kind of complicated, right? So what we would like to do, and I'm gonna put this over here, is make it kind of easy. So we're gonna define something called the transmissivity, and that is going to be equal to k times b. So this is going to end up being 2 pi t, and I'm gonna t times h2 minus h1 divided by ln of r2 over r1. So that is in fact the equation that we have. And so now you understand, hopefully, why we have this thing going on, and why it's different, and why you have to be more precise in such a case. So yeah, that's what that is. And basically I forgot to define my Q region, but our Q region would be here in this case. I would say it's I mean, you could say it's this way, but I'm gonna lean more on this side. But you have to understand that but our limits of integration are still h1 and h2 because it has to do with the total head. We know that at these points, at this point, and at this point, we know at this point the total head is h1 because the piezometer reading is telling us that. h2, this is, I mean, at point 2, it would have to be this because that's what the piezometer is telling us. So that's basically the case, because it's the total head. It's not the height. It's not the height. It's the total head. So keep that in mind. Let's go ahead and move on. Thank you for watching. And let me just say Q region. Now, so chapter 11, this is example problem number 1110, chapter 1110. So it says an unconfined aquifer is 300 feet deep, and its soil has a coefficient of permeability of 0.5 feet per day. A well with a 1 feet radius is drilled into the aquifer, and water is pumped out at a rate of 50 gallons per minute. The well's radius of influence is 1,000 feet. After pumping has continued long enough to reach steady state conditions, the depth of the water in the well will most nearly be what? So when they say well's radius of influence, they're talking about the point at which they think it levels off. So for all practical purposes, it starts when I say infinity, I have to be more specific because yeah, so this is unconfined, right? So you're gonna have this thing, right? And actually, let me. So you have this thing, right? And then so you have this thing, right? And this is the impervious soil, right? And then yeah, so then this thing goes through it. And remember, you're gonna have this thing. The reason why I'm drawing this out is because I want to be precise here. This over here, we're going to consider this the radius of influence, and I didn't explain this to you, but this is the radius of influence, and they're equal on both sides. We're going to assume that. So this is the radius because that's where it starts to taper off. If we were to use a gigantic R value, that wouldn't be correct, although it's conceptually consistent in the sense that we are taking infinity, but what you have to understand is that our head tapers off so that you don't have head as you go more and more. There's no difference in head as you go more and more. So the radius of influence is when it starts to level off. And that's important because if you use a bigger value than that, then you're gonna get a gigantic number and it's just not gonna be right. So if we use the equation, right, Q equals, if you go back, this was the equation right here, because we're using unconfined. So pi k, this, you know, so pi k h2 squared minus h1 squared divide by what? ln of r2 over r1. So this is simply just pi times, and they give you permeability. So 0.5 feet, and we have to be consistent with units, so just try your best with that. And then h2 squared. Let's see, the well's radius, a well with a 1 foot radius is drilled into. The depth of the water in the well. Okay, so we don't know what H1 is, but we know what H2 is. It says it's 300 feet deep, so we see here that this is 300 feet deep. Although it doesn't say it, we can assume that this is approximately 0, so that this distance is approximately 300 feet. So that it would be 300 feet. And then we don't know this one. And then divide that by ln of R2. Remember, R2 is whatever is going out there, so it's the radius of influence, so it's 1,000 feet, 1,000 feet. And then R1 is the amount of is the radius of the well, so that's going to be equal to Q, which is, we said, is 50 gallons per minute. Now we just have to solve for H1. So what's H1? Well, H1 is if we, let's see, I want to erase some of the stuff, but you just let me see. So I'm going to erase this. Let me just go ahead and arrange this stuff. So we have to find a way to convert gallons into feet cubed, because I don't remember what that was. Let's see. So how many? Let me see. Look it up. 7.481 gallons per feet cubed. All right, so now that we know that, we can do the rest of the problem very easily. So let me just get a calculator. Let's say how many. Let's just put say per minute for the time being. So actually, because there are how many minutes in a day? There are 60 minutes in an hour and 24 hours in a day. So that's how many minutes there are in a day. So that officially gets you into per day. That's going to be equal to 3.1415 times. I'm doing this because I don't have a freaking calculator. Oh, this, by the way, is that, so we're gonna have to square that, minus h1 squared times 0.5, because this is how many minutes there are in a day, and that gets you to day. So if you solve for h1, you get hopefully what we can get, I mean, we can actually do it. So hold on. 60 50 divided by 7.481. And that's to divide by 0.5 divide by 3.14159, and then 300. And then divide, and then subtract the 90,000 minus 6127, and then 83. So the answer should be 290. So these are just positive images. Really enjoy it. This is a guy pumping out a well, so this shouldn't be there, but anyway. Keep. So, you know, you got this, so these people are doing their own thing, you know, from Africa. They, like, can you theoretically